comenzar y la gente se irá sumando, ¿no? Good morning, everybody. Today we have a very interesting talk by Àngels Aran, and she will tell us about, well, you may explain since it's
okay.
a long title.
I can. Good morning, everybody. I will talk a little bit on the last updates, on the last results on solar energetic particles transport in interplanetary space. I say an update because recently 2 missions have been launched, so I will focus a bit on recent results from the 2 missions that have been launched to study the sun, that have gone closer to the sun, and a little bit of hints on what is needed to operational forecasting solar energetic particle events. So together with me, I have different collaborators. So these are, you can see them here. So Nicolas Besson is defended his PhD here at the department, at our department last year. He's now a postdoc at the KU Leuven and working on a H2020 project devoted to model solar energetic particle events that I will describe later on. Then Daniel Pacheco was also a PhD student of mine. He defended his thesis in April 2019, and he's now working at the Christian Albrecht University in Kiel, in Germany. He's on charge of the electron-proton telescope of Solar Orbiter, and he's now a member of the H2020 project devoted to exploit the data from Solar Orbiter, which is called Serpentine. And I think Blaise Anauja doesn't need a presentation because everybody knows him. He's ready always for a nice discussion. So I will start now with outlining a presentation. So I will briefly introduce all this subject. Then I will give an update on the recent observational studies. Then we can stop for the 15 minutes. And then I will finish with modeling particle and acceleration transport, recent developments, and the forecasting models, and finally give concluding remarks. So the sun controls the heliosphere and its activity, and the activity of the sun is what it drives the space weather. Okay, that would be the normal weather, but in space. And it's caused by the solar activity, in fact. So we have the sun, and then there could be a flare or a CME, or both at the same time. And these sources, both the flares and coronal mass ejections, which are the activity that happen at the corona of the sun, they can accelerate particles, which are the rays that we see here pictured in this graphic. So we see the sun and the solar activity that it's coming towards the Earth, and that could impact on satellites. Luckily enough, the Earth magnetic field protects us from all these solar storms, and then we don't usually have impacts on the humans or ourselves at the Earth surface. But there are different effects that I will describe later that could impact on our technologies and ourselves as well if we happen to be an astronaut in an extravehicular activity. So let's see. What is a textbook space weather storm? What it consists of? The solar eruptive event responsible for space weather storms from solar storms are solar flares that we can see here in extreme ultraviolet images from the Solar Dynamics Observatory at the Earth. So these are sudden releases of energy and particles, mostly protons and electrons, and that happen in a certain region of the solar corona, on the base of the solar corona. And then we have coronal mass ejections, which you can see here in the top figure. This is a coronagraph image, and what we see, this is white light, and we see the plasma blobs that are expelled from the corona of the sun, and they travel into the interplanetary space, coming to the Earth or to any other location In fact, you see here the plane of sky images of a coronal mass ejection, and they can surround the entire sun. So we can have explosions that projected in the plane of the sky, they can have 360 degrees. So once this happens, there is electromagnetic and particle electromagnetic emissions and particles ejected towards the interplanetary space. And what would be the timeline from those emissions to arrive the Earth? So in 8 minutes, we will have the extreme ultraviolet, X-ray and X-ray emissions reaching Earth, also radio, and that would already start disturbing the ionosphere, the higher levels of our atmosphere at the Earth. Then in 20 minutes and 1 hour, after the electromagnetic emissions, we can have the onset of the solar energetic particles. And then the most energetic will arrive in 20 minutes to Earth, and that would be the ones causing the problems from interruptions of radio emissions at the high in the ionosphere, or impact the electronics of a spacecraft mainly. Then in 1 and 4 days, the CME, the coronal mass ejected, would arrive to Earth, causing the geomagnetic storm. This plasma ejected, which are huge bulbs of plasma, would compress the Earth magnetosphere and provoke the geomagnetic storms at the Earth. So there are different effects that are coming from the sun, and I will mainly talk about solar energetic particle events that are the responsibles for effects on astronauts. So when we have protons above 30 MeV, they can impact and provoke and cause some nasty effects. Well, they could be responsible for even cancer, provoking cancer to astronauts. But then, which are less, which only happen, this type of events can happen only 10 to 20 times per solar cycle. Solar cycle is the solar activity of the sun is 11 years. Then we have that the lower energetic particles than 30 MeV can cause cell degradation of instrumentation on the satellites. And then the most higher energetic ones, above 70 MeV, can even reach the latitudes where transpolar flights happen. So the crew members should wear, and they wear, a device to control the radiation that they can accumulate over their career, for instance. Then when the CME arrives to the Earth, when the coronal mass ejection arrives to the Earth and compresses the magnetosphere, it can induce currents in the atmosphere, then reach the sun and the Earth and the sea, and cause the overcharging of electric lines, and they can cause blackouts only from time to time and for the biggest cases. But we have different local charging on the electric lines at different latitudes in the Earth, that they can happen more spuriously. So the companies of electricity, they do detect effects on related to solar activity more than once during the solar cycle. Then I have told you that 2 missions were launched recently to study the sun. Well, the first one was Parker Solar Probe. Parker Solar Probe was launched in August 2018, and it is designed, as you see here in this plot, to have an orbit that approaches closer and closer to the sun and the perihelia, and the maximum, the minimum perihelia it will reach will be 9.8 solar radii. So that means you have, let's say here, nowadays it's at the last perihelia was at 15 solar radii, which is 10 to 10.5 million kilometers. Okay. So it will go closer to the sun than any other mission has gone before. And it will provide us and will give us a lot of data to understand how the solar wind is accelerated and the early phases of the particle acceleration in events that we can capture now thanks to PSP, to Parker, closer to the sun. Up to now, since we are in a minimum of the solar cycle, there have not been big solar energetic particle events. The studies have been centered on plasma data. And one of the main results found so far is that what they are called the magnetic field switchbacks, which correspond to deflections, to changes, sudden changes of the magnetic field components that go together with a compressed solar wind speed. So there is an increase of the solar wind speed. For instance, you can see it here on the top panel. We see the magnetic field, the solar wind magnetic field at 30 solar radius. And this is the intensity of the magnetic field, and in color the three components of the magnetic field, the radial, normal, and tangential component. So what we see is a sudden change in the magnetic field direction that is accompanied with an increase of the solar wind speed. Here we have the radial solar wind speed component in the red curve, and there is an increase here. So there is an intense debate now, trying to understand well how these switches of the magnetic field directions are seen, because they were not detected until now for the young solar wind, so solar wind closer enough to the sun, and then they can have a proof, they can make us understand how the solar wind is accelerated. But this is, as I say, there are many models that are trying to get all this explained now. So we don't know yet exactly what causes the switchbacks. Then the Solar Orbiter mission was launched in February 2020. Solar Orbiter is equipped not only with in situ instruments to measure the plasma, the local plasma and magnetic field and energetic particles, but it wears a lot of instruments for imagining of the sun that Parker Solar Probe doesn't have. Also, the orbit of Solar Orbiter will allow us to see, to have images from the sun's poles, the north and the south pole, with unprecedented resolution that we never had before. Only Ulysses the Ulysses mission flew above the solar poles, but at 2 astronomical units. So it was too far to get detailed image data from the sun. So the main discovery so far of Solar Orbiter are what they are called campfires. Campfires are flares seen in extreme ultraviolet during quiet times from the sun, quiet periods. What we see here is an extreme ultraviolet image. These are line emissions of the iron 9 and 10. And the subsequent these other images here are zoom-ins of each part. So the red square here is what we see there, and the red square here is what we see here. And the campfires are these brightening features that we can see in this image. They give us a clue of the interconnection between the chromosphere and the corona, and the solar corona. So it's a way how hot plasma reaches the corona, and it starts to trying to explain how do we see the increase, why is that we have an increase of temperature going from the chromosphere to the corona. So we go from temperatures of thousands of Kelvin to millions of Kelvin. And these small campfires that happen, that they have been discovered more than 40,000, can be a mechanism to interpret how the corona is heated. So now I go to the main part of my talk, which is energetic particle observations. So here, as an introduction as well for everybody to know, in this plot, we depict they are depicted the different particle populations, energetic particle populations that we see in the heliosphere. So in this axis, we have the intensity of these particles, and the x-axis, we have their kinetic energy in MeV per nucleon. So the less energetic particles are those particles that conform the solar wind plasma themselves. So this is the solar wind population, electrons and protons, for the slow solar wind and for the high speed solar wind. Then we have the suprathermal tail of particles that go up to 100 kiloelectronvolts. And then less intense, they come the solar energetic particle events, those that are accelerated by flares and coronal mass ejections. We have these two populations. These are related to the particles accelerated and detected at the crossing of the shock that drives the coronal mass ejection. And these are accelerated earlier by the coronal mass ejection or the flares when they are close to the sun. Then we have other particle populations that are very less intense, but the most energetic, which are the galactic cosmic rays, which have 700 to well above 1 gigaelectronvolt. So these are the range of energies that I will be talking mostly, from 100 kiloelectronvolts to 100 MeV. And then we have another population which is quite important, which is the particles accelerated from the solar wind by corrotating interaction regions that I will later explain what they are. Here on the left, you have an example of a gradual solar energetic particle event. In the top plot, we see particle intensities from 400 for different energy channels that cover from 100 kiloelectronvolts to 100 megaelectronvolts. Here on the x-axis, we have the time, so it encompasses more than 2 days. The arrow marks the coronal mass ejection time, and then after a couple of hours, we start to see the particles intensities that start to increase until the shock wave driven by the coronal mass ejection reaches the Earth, in this case, 48 hours later, and then particle intensities start to decrease, especially those of higher energies. The bottom panels, I'm plotting here the magnetic field intensity and the polar and azimuthal angles of the interplanetary magnetic field. And for this event, it was quite smooth, and we only see the jump when the shock wave hits the observer at 1 AU. Okay.
Hey, Angels, maybe we can make a small break now.
Okay.
Okay, thanks. Are there any questions, comments?
Angels.
Yes.
About the deflection of the magnetic field in the solar wind, that there is this variation is on temporal scale of 1 or 2 minutes.
No, less. It's a matter of seconds, yeah.
Yeah, this can be produced by turbulence, or what kind of mechanism can produce that?
Okay, as I said, there are different theories, but one of the most that looks like that it's the one that will that will get through it, that will success, is that these are signatures of magnetic clouds that are expelled from the corona and get frozen into the solar wind plasma and travel to the interplanetary medium. So what we see here are magnetic flux drops, small magnetic flux drops embedded on the solar wind. So these are that would be like a small transients, like coronal mass ejections, but in a smaller scale. So they are compressing the solar wind and accelerating it a bit. And what we see here, it's just a geometrical effect when we see the magnetic flux drop that is, so the spacecraft is traveling through it. So then you see the changes, the rotations in both the switchback in the radial component here, because we go like in this case from negative value of the the magnetic field to a position when it is transverse, because then it goes to the radial component goes to 0, and then the polar angle goes from 0 to more than 50 or 60 degrees. So these are sudden changes due to the magnetic structure that could be embedded in the solar wind. Yeah.
One question is the dynamics of the magnetic flux lines is chaotic, or they are predicted by some model?
No, there are different models that can predict
it's not
flux
chaotic,
flows.
no?
I cannot, it's not, no, I don't think it is fully chaotic. What cannot be modeled is it's the plasma in the corona in a global scale with such details. That cannot be modeled. We need kinetic models for that. Mm-hmm. So there is not enough information to describe all this properly. So,
I see. We have a question by Jordi.
Okay, I just wanted to ask that I think, if I remember correct, so one of the key problems or key open problems in the in this area is the mechanism for heating the solar corona.
Yeah, exactly.
And I wanted to ask you, so that the things that these two missions are discovering, like campfires and this deflection magnetic field. So are they related to these? I mean,
yes.
Yes.
And they are related to this. So campfires are thought to be one of the mechanisms how the corona could be heated. But they are thought to be the tips of magnetic loops that they interconnect. So there is magnetic reconnection on them, and this magnetic reconnection effect would heat the plasma. So these are one of the mechanisms that could explain the heating of the corona, or at least it's pointing to that direction. What we need more we are waiting for images from the sun by the magnetogram and all this, when all remote sensing instruments will be operating. When the mission starts its nominal mission, it's still getting into the position for when the remote sensing instrumentation will open and start measuring. And with those, the structure of the photosphere and the corona will be better image. We will get better images from it. So that we expect to have, with that detailed information, more clues in order to interpret what's happening for the heating of the corona, and then also the acceleration of the solar wind, which is also something that it's not fully known.
May I tell something?
Yes, of course.
Yeah, just to complement what Angel said, is that there has been proposed the last decades several different mechanisms for the heating of the corona, but the problem is not the mechanism itself, but the efficiency of this mechanism as a heater.
Exactly.
So cam flares, it's a good candidate, but it is still a lot of work in order to derive or to realize or to calculate how efficient is the process, if it's not efficient to heat to 1,000,000 degrees Kelvin. That still takes some time, if it works, of course.
Yeah. But with both Parker Solar Probe and Solar Orbiter, we will get more information on the finer structure of the solar wind. And the more we learn about these finest structures, like these flux ropes I was talking, responsible for the magnetic field switchbacks, we will understand better how things are ejected from the sun and generate the solar wind. So I don't know if it will be everything fully explained. I don't think so, but we are expecting real advance on these subjects with all the information that we gathered from Solar Orbiter and Parker. And when I say we, I mean the entire solar community, solar physics community, not our team as well. Okay. Any other question?
Yeah, Àngels, you mentioned that most of the energetic particles are protons and electrons.
Yes.
What other components you have in a significant amount?
Heavy ions. Heavier ions, what we call heavier ions, are the remaining elements. So mainly helium, and then carbon, oxygen, and nitrogen, and up to iron. These are the species where we work most with.
Other questions? One more question I have is how many years these probes are supposed to be orbiting around or how many cycles are supposed to be functioning, you know?
Solar cycles, one. Solar Orbiter, the entire mission of Solar Orbiter, which is the one I know best, is 10 years. There's 7 years of nominal mission plus the cruise phase that we have passed now, and 3 years of extended.
What is the period of the orbit for each of the two probes?
The period, it's I think the Solar Orbiter is 6 months.
And they will measure only once, or they will measure each time they are in the...
No, every time that it's close to the perihelium.
Every time, but how many times they can function? That was my question.
I don't know exactly. I don't know, but probably 10 times or so. There will be open different windows depending on also on the position of Parker Solar Probe and the other spacecraft near the Earth, in order to get more information on the entire heliosphere. So it's not something that it's going to be fixed. There are different campaigns programmed, and there are more than 12 campaigns programmed so far. So it's not needed only that they will get images only when we are close to the sun, but also when Solar Orbiter is at different positions.
I see.
And Parker Solar Probe is measuring all the time, because they are in situ instruments as well as the in situ instruments of Solar Orbiter. They are measuring them all the time. Okay. So and the orbits of Parker are fast enough, are faster. But I think they are also about 6 months, because they are now in the 6th orbit, and it was launched in 2018, so 3 years. Yeah, so it goes more or less 6 months.
I see. We have a question by Roxandra.
Which is the question?
You're muted, Roxandra.
I figure okay, thank you. I have a question. Perhaps it's not exactly related, but how does measuring the solar wind better and the sun better impact spacecraft tracking? Do you know if it will improve the tracking of spacecrafts around Earth? Because we always have to correct for the sun to a certain degree.
I don't know. I don't know how that will help. Because it's based on data, on in situ data that you gather at 1AU, no? That you make corrections for that. So the other way, I think you can have. These two missions could have an impact on the information of the solar wind that you need, is that we get to know them better and then make improve the models for the solar wind predictions of 1AU instead. But this is something too far from my point of view.
Thank you.
Other questions, comments? Well, if not, maybe you may continue, Àngels, please.
Okay. So then, I was just about to finish the introduction of everything. So we have two sources of solar energetic particles, which are the flares and the shock waves driven by coronal mass ejections. Okay. Large events are related mostly to the shocks of in the front of coronal mass ejections, and the small events are related to solar flares. But in the largest events, we can have particles coming from both open magnetic field lines connected to flares and from the CME shock front. Okay, so the two phenomena occur not simultaneously, but yeah, almost simultaneously, but they are not operating all the time. Okay? So solar flares operate at the beginning of the event, and then we have the particles accelerated by coronal mass ejections mostly. So far, these are observed. These are the two orbits of solar orbiter, and we have plotted here the particle intensities from protons and electrons. Electrons are plotted inside, protons outside. So you can see there has been little activity, at least in the first year. Now in the second year, we have more events. And in April, they happened quite a couple of them that were more intense. But so far, the biggest one was in November 2020. Okay, so these are the different fields of view of the solar energetic of the detectors, of the particle detectors from solar orbiter. In this map, what it's plotted is the magnetic field vector, the pointing direction gathered from the Helios spacecraft mission. That Helios was launched between 1974 and was operating until 1985. And for the measurements of the Helios spacecraft, we can see where the interplanetary magnetic field it's pointing most of the time, which is along the interplanetary magnetic field lines, which follow a Parker spiral. So it's an Archimedean spiral with a 45 degrees inclination from the radial direction of the Earth. So we have here the sun, and these are the two directions marking the inward and outward solar magnetic field when it extends to the interplanetary medium. So the two telescopes, the EPT and HET, the energetic proton telescope and the high energy proton telescope of the particle detector suite, are pointing in these sun anti-sunward directions. And then we have two other look directions at the north, towards the north and the south poles of it. Then we have the STEP instrument, which is for low energy particles, that it's only pointing in the main direction, pointing outward from the sun. And then there is this SIS instrument that measures heavy ions, that it's pointing in the main direction, looking at the sun, and for a west and another western looking direction. What I will be talking mostly about are data from the energetic part and for the electron proton telescope and HET in the next slides. So this is a summary of the at the top electron data, ion data gathered by Solar Orbiter in the month of July 2020. So we see all these events are rather small compared to the one I was showing you before. Here the energies only go from 10 kilo electron volt to 2 mega electron volts. So it's really rather small. The previous one, if you remember, went from 100 kilo electron volts to 100 mega electron volts. So here the particle enhancements are only seen by very, very low energies. But the instrumentation has a so nice resolution both in energy and time that we can get a lot of details from the origin of these energetic particle events. In this top panel, I'm showing radio emissions. So this is a type 3 burst observed by Solar Orbiter. And then here in this panel, I'm showing it's showing the intensities in colors. And here on the y-axis, we have the energy as a function of time of the particle. So we go from 5 kilo electron volts to 500 kilo electron volts. These, if I am not mistaken, are electrons. And with all this, what we can see here, it's a plot that we can follow just because of the different speed of the electrons, we can infer when these particles were released from the sun. So we follow the onset of these particles from this line, getting when they were released, which is marked by this arrow, and it coincides with the time when we get the radio emission from the activity of the sun that generated from the type 3 burst that generated the flare that generated this event. So, and what we see here also in the bottom panel are the directions of the particles that enter through each of the 4 fields of view of the detector, with the direction with respect to the magnetic field. So what we see is that we have more intensity, so particles are coming aligned with the interplanetary magnetic field. Okay, then we could also study different small events. This is an ion event that occurred on 19 June 2020, and serves, and in the top panel you see the particle intensities. These are again very low energies, from 18 to 800 kiloelectron volts. I'm saying ions, but they are mostly protons in this case. And then together with this, at the same time, the high energy detector measures higher energy particles, which are since there were no solar energetic particles to these energies, these are galactic cosmic rays measurements from 17 to 20 MeV. And what we see is a decrease of the galactic cosmic rays measurements that coincides with an increase of the magnetic field intensity all the time. So we see that there is a modulation of the galactic cosmic rays with the interplanetary, with local increases of the interplanetary magnetic field. We studied these decreases of the galactic cosmic ray intensities. In purple, you see that the variation of the particle intensity, the percentage of variation of the particle intensity of these galactic cosmic rays measured during the month of June, during this event that we were studying, compared to the same structure observed at the interplanetary magnetic field, compared in the next solar rotation. So what we see is this in gray, the galactic cosmic ray decrease that happened on the following solar rotation. And what we see is that the decrease during the 19th of June event, when we have the increase of the low energy particles, it has the same structure. It decreases in the same way. So we have that this the depression of the galactic cosmic ray intensity is due to a magnetic structure that is co-rotating with the sun. Also, we studied then the directions and the angular distributions of the low energy particles detected by the electron-proton telescope. This is the data gathered by the sun field of view, so the telescope that is pointing towards the sun. This would be the data gathered by the anti-sunward field of view. So we see nothing, there is not an increase of the particles. And then this is a plot of the south field of view. And the north field of view saw the same as the south. So there is a small increase of the particles here and later on there, which would correspond to this time here and these particles seen there. This information allowed us to derive the anisotropy, the sun anti-sun anisotropy. And we observed that there is a positive anisotropy at this time when we observe the maximum intensities of the low energy intensities. And this is, so we believe, and comparing with previous events measured at 1 AU, that this is due to local acceleration of these particles in the solar wind. What would be the structure responsible for that? Well, here you see in this plot in purple the solar wind speed. What we see is that the solar wind speed was slow, dominated by the slow solar wind, and then it arrived a high-speed solar wind stream, jumping from 200 kilometers per second to 450 kilometers per second, more or less. This high-speed stream came accompanied with a compression in the magnetic field that we see here, which shows different rotations and changes also in the azimuthal component of the interplanetary magnetic field. This is a signature of a rotating interaction region. And well, this would be a stream interaction region when a fast CME stream intersects the slow CME. That since we detected that it happened in the next solar rotation in July, we can say that it's co-rotating. We also look back into May and April, and we saw these signatures again. So there is a co-rotation this is a co-rotating structure from April, May, June, and July, at least. So the future is that we see here is that we have this local acceleration of particles there, that it's accompanied with the depression of the galactic cosmic rays. There are some signatures here of the anisotropy that we cannot explain, and also it's difficult to explain how these low energy ions were accelerated too. So we cannot discard that this little CME that we saw with Solar Orbiter could be the responsible, who could be also accelerating some particles when arriving to the Solar Orbiter location. So we need also Riemann sensing observations in order to fully interpret all this data. So these co-rotating interaction regions is that we have a fast solar wind speed catching up with a slow solar wind speed, and then in these regions, when the fast wind overtakes the slow solar wind, so when the fast wind is decelerating, and the slow solar wind is accelerated and the fast wind is decelerated, there are created two compression waves, the forward, that would be here in blue, and the reverse compression waves. And in these compression waves, we can have particles accelerated. That would be different from the mechanism that we observe here, because this is just local stochastic acceleration due to second order Fermi process. But we also can have in co-rotating interaction regions acceleration by the compressional waves in a first Fermi order process. And this is what we observed in one of the events that I will explain you. There is a co-rotating an energetic particle event associated with a co-rotating interaction region that we modeled for, that was observed in 19 September 2019, that we modeled it. And to model it, we use a focus transport equation to model the transport of the energetic particles. This model was developed by Nicholas Besen in his thesis. And it starts from the Blasov equation, and then we model the different aspects. So we have the solar wind stream, the solar wind has the streaming of the particles, focusing, mirroring in the interplanetary magnetic field. We model the acceleration of the particles and the diffusion due to turbulence. Okay. For doing that, we consider, we move to the guiding center drift theory, sorry, to the guiding center theory for describe the movement of the particles and average through the zero phase of the particles. And with that, we get the modeling of the diffusion and the turbulence in the interplanetary magnetic field, which is treated in the regime of the quasi-linear theory. We also model.
You have 2 minutes.
Okay, then I will go fast to finish. So what it's described in the model is the larger scale modifications of the transport of the particles. And for that, to get the larger scale solar wind, it's use a 3D MHD model that can model the co-rotating interaction regions and CMEs. And then we model the particle transport diffusion using the quasi-linear theory and treating the turbulence on the magnetic field as in the linear theory. So for that, if we inject particles, we can inject particles on the shock waves. We can get particle acceleration and transport it there. So in gray shades, you see here the solar wind speed and the intensity in the brown shades. So I changed now to the event that we modeled. So this event was seen by stereo A at 1 AU and by Parker Solar Probe at 0.56 astronomical units. So we could model this event, the rotating interaction region, for 2 spacecraft. Okay. In these panels in blue, you have the data from solar wind velocity, density, and magnetic field, and on top of it, the simulation performed with the Euphoria model, the 3D MHD Euphoria model. We took a magnetogram, and then it's propagated into the inner boundary conditions of the Euphoria model at 20 solar radii, and we modeled the plasma, and the plasma is modeled for that. So we reproduce the solar wind speed, density, and magnetic field at the spacecraft at 1 AU, and also the Parker Solar Probe. We reproduce the data that it's observed, and there is here a huge data gap, as you can see. So then we injected particles at the compressional waves that they are detected as the negative divergence of the solar wind speed. Then we inject these particles here along these regions with negative divergence and do the simulation for 12 days. Okay, so there is a map of the 3D heliosphere showing where the forward and reverse shock waves of the rotating interaction region, where they are, and here and there as well. This would be the equatorial plane. So for that, these are the the intensities observed by the stereo A spacecraft, and these are the modeled intensities. And you can see we can reproduce several features of the observed intensities rather well at 1 AU. So the 2-peak structure, the right onset of the particles, and then also the fast onset of the energy, the low energy particles, and the second peak and the more gradual energetic particles that is observed at stereo A. So finally, we also look at the particles intensities that would have been observed by Parker Solar Probe. And what we see is that if the MHD model would have been better in capturing the solar wind for Parker, you see there is this data gap that we could displace 18 hours, and then we would get the right increase of the modeling of the decay phase of the solar wind speed. If we would make this time shift on the intensities that we gathered, then you get the dashed line that trace perfectly well the observed energetic particles seen by Parker Solar Probe. With all this modeling, the advantage of this is that we get a 3D picture of the distribution of the energetic particle intensities. Here you have a spherical slice at 0.5 AU of the entire of the heliosphere. In color shades, we have plotted the solar wind speed. So blue is the slow solar wind, red is the fast solar wind, and here we see that the particles, which are in gray shades, so we have contours of particle intensities, distribute in these 2 peaks that we were observing, in the slow and in the fast solar wind. And here is the same at 1.5 AU. Here we see that the particles are mostly accelerated farther from the sun, where these compressional waves develop to shock waves, so where the efficiency of the particle acceleration is larger. And these particles here travel towards the sun, and this is where we detect them at 1 AU mostly, and by Parker Solar Probe. But also we have local acceleration at Parker Solar Probe distances, and this is what was not modeled before. So we were the first ones to do this. Then there is I was mentioning before that there has been only one large SEP event observed, and this is how Parker Solar Probe and Solar Orbiter can help us. Here in red we have data. We have the satellites orbiting around the Earth, and this would be a stereo A here in red. What we see here in these panels, the top panel, we see the increase of the flux of electrons, and the bottom panel, we see the increase of protons at different energies at 0.5 MeV and more than 10 MeV. It changes on the different detectors. But what we see is that there is a slow increase for the Earth and a more rapid increase for stereo A. But we would have missed entirely this event if we wouldn't have had Parker Solar Probe here, that it's seen the most energetic part of the event, so where the most energetic particles are accelerated. So we have this huge increase here of the particles. And then Solar Orbiter, which is also quite well connected. So we can see a rapid increase of the 10 MeV protons in there. So adding these two platforms to have more information on the heliosphere will help us to forecast, to better constrain the initial boundary conditions from our models and get better predictions of the SEP events. But so far, all these state-of-the-art models, that the ones that we have, that I was presenting to model in 3D, the global 3D structure of these events, coronal mass ejections, rotating interaction regions, and solar energetic particles, they are not ready yet to go through the full chain from the sun to 1 AU. Because I was telling that, for instance, before that the Euphoria model, the 3D MHD model, starts at 20 solar radii from the sun. This is 0.1 AU astronomical units from the sun. But all these high energy particles are accelerating within that 0.1 AU distance from the sun. So far, to model and to apply events for forecasting, it's 5 minutes.
We have already over time. How much time?
2 minutes. I'm finishing in 1 minute.
Okay.
It's not fun. So we are using still 2D MHD models, like the ones we developed a few years ago, for which we model the transport of, we model the propagation of the shocks in 2D, and then we get a 1D particle transport code that accelerates the particles in this point, which are connected, magnetically connected with the observers, and we get the modeling of the intensities for different energies. With that, we can build, we can start building a system to try to forecast solar energetic particle events. But to do that, just is the message that I want to convey, is that there are needed 3 things for these operational systems to work. We need first a model to predict when a solar flare and a coronal mass ejection will be produced. And this is the most difficult part. That's why we need data from Parker and data from Solar Orbiter to better improve our knowledge on these aspects of the sun, how the solar activity is generated, right? Because nowadays, all this part, the modeling of the forecasting of solar flares relies on machine learning techniques. Then the next step is, okay, we have an activity and a solar flare is predicted. Will this accelerate particles? Will the coronal mass ejection accelerate particles? For this, we need a model to forecast the solar energetic onset of the particles. There will be an event or not. And this is done using a statistical model. So it relies on the last decades of data gathered on solar energetic particles. And finally is, okay, we will have an SEP occurring. How this SEP event will look like, which is the intensity they will gather at different energies. Will they be, do I have to put my astronauts inside the International Space Station, or they can go on away and out of it and do their operations in space? What can be done? For this, we need the models I was presenting before, no? The solar energetic particle event models, that's like the ones we have. But to make all this improve, like this is an example for one event. We have this data here. This is the prediction with 2 levels of confidence, 50% and 90% confidence levels for 4 different energy windows of 10 MeV, 30 MeV to 300 MeV. To improve all these models, we need to improve the other our science or knowledge on the science ruling the sun. Okay, and this is all what I wanted to say. So thank you. And sorry for taking long.
Well, thank you, Àngels, for this interesting talk, and it's really an impressive work. Let's see, we have a question by Jordi.
Yes, sorry that we have little time for questions, but actually I just wanted to go back to the question that was asked by Ruxandra before, that very interesting. And basically, I think that, so one question is, whether the SolO right, when it interacts with any spacecraft, it affects its trajectory through the force, the momentum of the wind. And I think also for, let's say, asteroids, how it affects things like asteroids. But then in relation to this, right, in the LISA mission, we also have spacecraft, and inside it, there is a test mass. And so then, of course, the SolO is going to interact with the shield, everything outside, and then it'll affect the spacecraft. But then this is supposed to protect the test mass. But then I think you've been working on the impact also on the test mass, even when it's protected, right?
Yeah, but it's not really the solar wind that it's going to affect. It's more the galactic cosmic ray background that is the one that, because we are seeing that for the test mass will be affected mostly for particles between 80 MeV and 300 MeV. And
which are galactic.
Which are mostly the galactic cosmic ray population on that, and some sporadic solar energetic particle events, and can reach up to those energies.
Okay, but if you worry about...
But the galactic cosmic ray is always there.
Yeah.
And that will be the largest population impacting the test mass of LISA.
But if you worry about the effect on the outside shield, right, or any spacecraft on the surface, then I suppose it is the solar wind that it has.
You have the ones that have the effects that have more danger on that are not the ones from solar wind, which can cause solar cells degradation. Okay, but solar wind is composed by very low energy particles. So the most undesired problems will, like single event upsets or single event effects, they will be caused by the solar energetic particles.
Okay, but one thing is the effect on degrading solar panels or human health, but the other is changing the momentum. So actually the force acting on a spacecraft just directly from momentum given by the solar wind or anything else, right?
Yeah, that has to be the solar wind, yes.
So that's what I was wondering, I guess, or maybe Ruxandra's question.
But I'm not sure how about that. I mean, I don't know exactly how. If I haven't heard that that CM is strong enough would change the solar wind direction. I mean, could have enough pressure to change the solar wind panels, the solar cell panels direction.
Okay, are there any other comments? Well, if not, let's thank Àngels again for this very interesting talk. And we see you next week for our last talk in this series of internal seminars. I hope you see you all there, and thank you very much for participating. Thanks.
Thanks to all for listening.